This recording is part of the recordings that cover hemodynamics, and specifically now we're going to be looking at capillary exchange. Now, gases and nutrients and waste products are exchanged between the capillaries and the blood in the capillaries and tissues three different ways. And there's a reason for exchange. You need to deliver nutrients and hormones to tissues. You have to pick up waste products. So we want this exchange to take place. Remember, capillaries are thin-walled, so they allow that exchange to take place. Well, there's different processes that are involved. Simple diffusion. So things like gases, they're going to, or anything that's lipid soluble, can easily cross the membrane. They're going to go from high concentration to low until it reaches equilibrium. You may have facilitated diffusion, where you're going to use some sort of transport protein to move things across the membranes. You have, depending on the type of capillary, some will actually, instead of going across the membrane by diffusion, you may have this right here, bulk fluid flow. But before I mention that, I want to mention vesicular transport. So remember, vesicular transport includes endocytosis and exocytosis. And if you don't remember what they are, you need to review your AMP1, because you should have learned about various transport processes. So these are different examples of active transport. So you can have things in capillaries involve endocytosis, where things are going into the cell, exocytosis, where things are going out of the cell. Last example is something called bulk fluid flow. It involves filtration. So filtration was another process that you learned in AMP1. It was a passive process. It was because of the force of that blood, because of hydrostatic pressure, is going to force fluid, and things that are in that fluid cross those membranes through the various pores. And so pressures really determine bulk fluid flow. And it's not only hydrostatic pressure where you get filtration, is we may have absorptive pressures. So we're going to be looking at the factors that can influence the amount of fluid and things that are in that fluid that can move across those membranes. So what you have here is a picture. It's one of those classic pictures that depict what's going on in the capillaries, where it's what we refer to as an idealized capillary, where they show you that at the arteriolar end here, you see this big old arrow that's saying filtration. So filtration is, it's telling you we're favoring movement of fluid across that membrane into the tissues here, into the interstitial spaces, and eventually into the cells. At the venular end, which you see over here, we see the big arrow going into the vessel. So it's saying at that end, the pressures favor absorption. Now, this is a depiction for an idealized capillary. There are some capillaries in our body where we have only filtration, such as the glomeruli in the kidneys. So that has only filtration. Things like in our GI tract, intestinal mucosa, the villi in the small intestine, say, for example, you have absorption, because we're going to be absorbing nutrients. So it depends on what do you have, what type of, it's the balance between various forces. And we're going to be talking about, and the forces have to do with pressures. And what pressures favor filtration, what pressures favor absorption, or in some cases we call it reabsorption. So I'm going to look at, give you some terms for different pressures we need to look at. So there's 4 pressures we need to be aware of. 2 of them are hydrostatic, kind of have to do with that water. And hydrostatic pressures, I want you to envision, so if I have, I'm going to just look at the end of this tube, like right here. If I'm water inside the tube, I'm pushing this way, okay? If I'm outside the tube, that's one water, I'm pushing that way, okay? So it's the pressure of that water. And if I'm an osmotic pressure, you should have learned about osmosis and osmotic pressure. And osmotic pressure is that pressure that's going to want to prevent fluid from moving across the membrane, because in what's driving water moving across of membranes are osmotic pressures. Water wants to go from its high concentration to low concentration until it reaches equilibrium. And so the way I envision it here, so if I draw my vessel again, if I'm an osmotic pressure, and I'm just going to put this here, say I'm an osmotic pressure, it's wanting to draw things towards it. If I'm out here and I'm an osmotic pressure, it's wanting to draw fluid out. So think of hydrostatics want to push away, hydrostatics like pull it towards you. So let's think if we can kind of reason out these different pressures and what's going on. So we're going to start with the first pressure, which is your capillary hydrostatic pressure, which is often abbreviated like this. I'm just using this abbreviation. So this is your capillary hydrostatic pressure. Think of it as your blood pressure. And the average pressure in the capillaries, in the systemic capillaries, is 17.3 millimeters of mercury. And you notice the arrow, it's going out. That favors filtration. Okay, so that favors filtration. So you've seen the arrow moving out of the vessel. Now you have over in the blue arrow, down here, you see this one here. That represents your plasma colloidal osmotic pressure. And we use the abbreviation pi p. You don't have to use that abbreviation, but it's going to become easier later when I show you an equation. So that represents the osmotic pressure in the blood, and that osmotic pressure in the blood is usually due to the presence of plasma proteins. Those proteins are charged. Water is attracted to them. So you notice this favors absorption or reabsorption, depending on where we are. So it's wanting to draw water into that vessel. Then we have some interstitial fluid pressures, because we have fluid in the interstitium. That's the fluid between the cells and those blood vessels. So I'm going to do this one first because it's easier. So this here is the interstitial fluid colloidal osmotic pressure, which we abbreviate as this. Now the reason why we refer to those osmotic pressures as being colloidal, because those things that are dictating the osmotic pressure is they're not dissolved, they're actually in suspension. Like those proteins are suspended in the blood, they're not dissolved in your blood. So you may have some proteins in the interstitium, and that's going to draw fluid out of that blood vessel. Say, hey, come hang out with me. And so it's wanting to draw fluid out, so this favors filtration because it's wanting to leave that vessel. Now the last one is a little tricky. So I have drawn two different arrows. Both of these represent interstitial fluid hydrostatic pressure. So you have a fluid in the interstitium, and you'll notice I have the arrow like this. And this is the abbreviation for the interstitial fluid hydrostatic pressure. If I express that value as a positive number, it's telling you it favors absorption, okay? So you're seeing it's pushing fluid into that capillary. However, if that value is expressed as a negative number, it's subatmospheric. This, if I draw it this way, this means it favors filtration. So it depends on where you are in the body, if that pressure is a positive value or a negative value. And so I'm just going to tell you kind of the average pressures when we do the systemic circulation for these. I already did this one here. This one is 28 millimeters of mercury. the interstitial fluid colloidal osmotic pressure is 8. And this one, typically, in the systemic circulation is a -3 millimeters of mercury. So it's telling you it's favoring filtration. Well, the question is, when we're looking, these are the average values in the systemic circulation through you're talking about the entire capillary. Do we have a net movement of fluid out of the vessel, or do we have a net movement of fluid into the vessel? Do we favor filtration? So think of that as being out. Or do we have absorption, which favors fluid moving in? So we're going to give you an example. So these are the values that I just gave you. Here is an equation, and it's what we call Starlings equation for bulk fluid flow. Ignore the KF for now. So what they've done is they've pretty much put outs minus ins, and that's the equation. If you plug in the numbers, if you so choose, if you plug in the numbers and you do the math, this is the value that you should get. Notice that value is a positive number. If that value is a positive number, it's telling you it favors filtration. This filtration coefficient, that's what that means, filtration coefficient. That's determined by the type of vessel. Different vessels vary. It tells you kind of how permeable that vessel is. Gives you an idea of how much fluid moves across per minute for every millimeter of mercury pressure gradient that you have. So just to make it easier on you, if I say for this particular vessel, the filtration coefficient is 1 mil per minute per millimeter of mercury, and I multiply it by 0.3, what's the flow rate? You'll have 0.3 mils of fluid move across that membrane from inside to out. It's going to filter out per minute. Now, could that be a problem if I'm losing 0.3 mils every minute from a capillary? Yep, because you lose all that fluid, your blood volume is going to go down, your blood pressure go down, there'll be a problem. So we do have lymphatic vessels that will pick up that leaked out fluid. Lymphatic system, one of the key things it does is not all about immune system. I mean, it's very important that it's part of your immune system, protect you against disease, but it's very important in maintaining fluid balance. So any fluid that's leaked out, we can get it back into your circulation using our lymphatic system. Now, what about, here's another scenario. I'm going to give you some other values. So here, I'm giving you some different values. If you do the math, you'll get a minus 10 millimeters of mercury. So if it's a negative number that you get, that tells you it's favoring absorption. Okay, so this favors absorption. And those values are actually real life values. These are values coming from what we call the peritubular capillaries. They're in your kidneys. And the glomeruli is where filtration takes place. But we need to recover any things that were filtered that we need to get back. And what's going to happen is you want those peritubular capillaries to favor absorption. And so this is what we get. We get a net absorption pressure of 10 millimeters of mercury. That negative tells you it favors absorption. I'm going to tell you the filtration coefficient for those vessels is 12.4 mils per minute per millimeter of mercury. And if you do the math, you would get, that minus 10, we're just telling you, it's telling us the direction. You don't have to use that negative in your final number. It tells you there's 124 mils of fluid being absorbed by those capillaries every minute. And what if I tell you that your filtration in your glomeruli, I can't even say it, the glomeruli favor filtration, and it's a net filtration pressure of 10 millimeters of mercury, but in the glomeruli, their filtration coefficient is 12.5. If I multiply by 10, your filtration rate in the glomeruli is 125 mils per minute. Now just think, if you didn't reabsorb that, you would lose your blood volume very quickly. And so what happens is we reabsorb all of that except for 1 mil per minute. So if you someone does the math, you can get a rough idea how much urine you're producing every minute. Of course that can vary, but I just wanted to show you that. I want to show you another way of looking at these values besides memorizing an equation to allow us to determine the direction of fluid flow. Because I want you to think just more conceptually. Is if I come back here, what I do is I make a table. Outs and ins. The pressures that favor out, which is filtration, so I'm just going to put an F there. And ins would be the ones that oppose filtration or favor absorption, or we can say reabsorption. When I do this, I don't have to worry about any negative values. The negative value that you see here only tells me which column I need to put in. So I want to do is I want to put all the pressures that favor filtration. This one does. That one, because I told you is a minus number, so I'm just going to put 3. And the 8. The only one that favors absorption is this one. It's 28. So if I do the math, this is 28 millimeters of mercury. What is this one? 28.3 millimeters of mercury. Which value is bigger? That one. So it's telling you we're favoring filtration. And the difference between them is 0.3 millimeters of mercury, which you just said, see here, using a different equation. That's just one way of doing it. If I do this one, if I do the outs, and I do the ins, so 13. Now this one, notice, this one is a positive value. So this being a positive value says it opposes filtration, so I'm going to put it over here. The 32 I'm going to put over here, and the 15 I'm going to put over there. So when I do the math, it's 28, 38. Which one's bigger? The forces that favor absorption, the inwards. Notice difference. There's a 10 millimeter of mercury pressure difference between them, and so you see that right here. So 28 minus 38 is minus 10. So that's just another way of looking at it. Okay, so what I want to do in a separate recording, it's going to be relatively short, is I want to look at some clinical scenarios that could affect, that would result, I should say, result in abnormal imbalances of those forces. It can lead to something we refer to as edema. So I'm going to do that in a separate recording.